my beautiful AP Calculus students. We are getting ready to embark on integration of the natural log function. So this is section 5.2. But before we start this log rule for integration, I want to review a little bit with 5.1. Kind of simple like, the derivative of the natural log of u is equal to 1 over u multiplied by the chain rule, which is the derivative of u with respect to x. And as you know, a lot of people like to call that u prime over u. This power right here is on your denominator, and the derivative of that power is sitting on your numerator. That's what this is saying to you. This power, whatever your u is in that set of parentheses, that power has to be positive. And the reason it's positive is because your base is e. You can see that because you're given a natural logarithm, and the base is presumed to be the e if you write natural log. So e to any exponent, I don't care what your exponent is, so I don't care what this is equal to, has to yield a positive power. E is positive itself, it's about 2.71, so to raise to any exponent, even 0. E to the 0 is 1, e to the negative 1 would be 1 over e, e squared, and so on. I'm never going to take a base of e, raise it to any exponent, and come up with anything other than a positive power. So it's really important that we understand that what's in these parentheses right here is presumed positive if we are applying a natural log to it at all. Okay, now when we go backwards, that's going to matter, because maybe this part of the problem, we don't know that something is positive. So we want to go backwards, we're going to have to use a natural log, but we're going to have to make sure that whatever that u is, it is a positive value, and we will denote that with absolute value symbols to make it positive. So we have one theorem in this chapter, in this section of the chapter, and it's your log rule for integration. And it says pretty much easily, just simply let u be a differentiable function of x and that's of course so that we can do du dx. So let u be a differentiable function of x. The first part of the theorem is pretty simple just in terms of x, and the second part of the theorem we get in terms of u. So the integral of 1 over x with respect to x, or the antiderivative of 1 over x with respect to x, is the natural log of x, and then possibly plus the constant. However, remember what I'm talking about here, whatever's in these parentheses is supposed to be positive. So in order to make it positive, we just wrap that x, swap that power with a set of absolute values instead of parentheses this time. So even if x itself were negative on your denominator here, once you put it inside here, we're going to make it positive so that the natural log can actually apply to it. And this is our log rule for integration with x. And to put that in terms of u, it's just the integral of 1 over u du now is equal to the natural log of the absolute value of u plus some constant. And that's it. I mean, you can tell that the integral of 1 over x dx is just a special case of the integral of 1 over u du, because the derivative of u with respect to x is simply a 1. All right, and now we will hit a whole bunch of example problems. So all of the example problems that I'm doing, the natural log integration process here is going to be part of it. It doesn't mean it's the only thing sitting there. Not all the questions are going to be this simple right here. Sometimes they're actually kind of difficult to even identify, okay? Sometimes it's let me try this and see if this is going to work. No, it doesn't work. Let me try something else. And you're going to see some of these questions, you'll be like, how would I ever know that? And I'm the same way. How would I ever know that either? I wouldn't know it if somebody didn't tell me. So we're going to go ahead and figure out as much as we can, and then I'm going to give you a few tricks as we go along. So I'm going to erase all of this information here. We'll keep the title up there for 5.2. And let's start with some easy integrals so that we can just get the idea of what's going on with the process. Here's example 1. I would like to integrate, and I'm going to stick with a integral that has no upper and lower limits so that we don't have to worry about doing the fundamental theorem of calculus and substituting them both in and subtracting. So I just want to get the idea of the substitution down for you. Okay. So we have an indefinite integral. It's not definite because I don't have definite upper and lower limits. 3x squared minus 5. All right. Some keys me into this being a natural log problem is that I have a denominator whose degree is 1 degree higher than the numerator. So I'm thinking if I were to take this derivative of this denominator, and I could be off by a constant multiple. In this case, I have it perfectly, right? The derivative of 3x squared minus 5 is just 6x. So 3x squared minus 5 is on your denominator. Its derivative is sitting on your numerator. This is definitely one of those natural log problems, and it's real simple to notice this particular one. However, I'm going to go through the u substitution with the whole problem anyway. So I'm going to say let u equal 3x squared minus 5. And now my derivative of u will be the derivative of this side also, but this is with respect to x. And du is equal to 6x dx. I see that right here. I think I'll be nice and easy with you guys and pull the 1 to the outside, multiply by 6x dx. Do you see that I did nothing to change the value of anything in my integrand? All I've done is pulled it apart so I can see 2 pieces. So this is 1 over, and 3x squared minus 5 is my u, and this is my du. And now I have 1 over u du. I'm right back to Theorem 5.1, or Theorem 5.5, I'm sorry. And I can say that this is the natural log of the absolute value of u plus c. Bring my u back into the problem. My u was 3x squared minus 5 plus c, and I'm finished right there. This is the end, and it's quite an easy question right here. If I wanted to check this problem, I would just come over to the side and say, okay, well, let me get the derivative of what I think my answer is, natural log of the absolute value of 3x squared minus 5 plus some constant. Take this derivative, and I'll see if it turns out to be my integrand right here. Well, in order to take the derivative of the natural log, that's your section 5.1, we're just finished with it. The power, whatever the natural log is being applied to, goes on the denominator, 3x squared minus 5. And then you look here, you don't look back here, you look here and you take this derivative, which is 6x. And the derivative of any constant is just 0, so this gives me 6x over 3x squared minus 5. And that was indeed the integrand of your original problem, so we have a check. And sometimes it's not necessary to go to the side and do the physical check. You can kind of mentally hit that in your mind and say, yeah, that works. Okay. So example 1 is done. Let's see how many more examples I can hit here kind of quickly. We will go for example 2 now. I have the integral of a fraction 4x cubed minus 3x over 2x to the 4th minus 3x squared. This one's taking it just a little bit further, it's given it a little bit more thought process. I still see some fractional value, which keys me into that natural log idea again. And what I see on the denominator is a degree 4. What I see on the numerator is a degree 3. I'm thinking, hey, I wonder if that numerator happens to be the derivative of the bottom exactly, or maybe off by some constant multiple so I can do my u substitution. So when I look at this denominator, I take its derivative and I get 8x cubed minus 6x. And I think 8x cubed minus 6x, that says 4x cubed minus 3x. The numerator is exactly half of what the derivative of the denominator is. So half is a constant multiple, I'm going to be good to go with the u substitution. So I'm going to go to the side and I'm going to say let u equal 2x to the 4th minus 3x squared. And basically my thought process just gets written down. My du becomes the derivative of 2x to the 4th minus 3x squared, which is 8x cubed minus 6x, all with respect to x. Now I don't have an 8x cubed minus 3x. But I notice, and you have to notice, no one can help you notice, it's got to be on you. You have to notice that if you take this derivative and divide it by 2, you get that numerator. So you take the derivative, divide by 2, this gives me half of du is going to equal 4x cubed minus 3x with respect to x. So instead of rewriting and pulling this apart, I think what I'm going to do is just circle this piece for you and say all of this, the 4x cubed minus 3x dx, is the same as 1/2 du. And what's on the denominator here is your u. So now we're going to rewrite this integral all in terms of u. I end up with 1 over u times 1/2 du. And remember, by the way, when you do your substitution for u in terms of x, and you come back over here and you make all your substitutions, you have to have this statement right here all in terms of u's, no x's. You cannot mix the x and the u at this step. So you can't do one piece and then do the other piece. You've got to do it all at once. Now this 1/2 will move to the outside of my integral. I have 1 over u du. That is my theorem 5.5 I just talked about, natural log of the absolute value of u plus c. And I have to put my x back in. So I have 1/2 natural log of the absolute value of 2x to the 4th minus 3x squared plus c. And I'm finished with this problem. I just want to mention one little thing here with you. If this, maybe that doesn't even work. I was going to say to you that if this had been a plus sign, well then something to the 4th plus something, that same something squared would have to be positive, but maybe x is 0, so I can't say that. This is not always positive. I was thinking maybe that the absolute values were useless, but they are necessary because if x happens to be a 0, I can't have the natural log of 0. It does not exist. It's not defined because 0 is not positive. Okay, so we're good on example 2 here. All right, I think I'm going to cut this video right now. We're going to finish up a few more examples on the future videos, and we'll say that's it. If you want to do your check on this one, I think I'll leave it up to you. You go ahead and take this 1/2. Put this on your denominator, take its derivative, put it on its numerator, and then cancel your 2's, and you're going to end up with that same thing right there. All right? Talent out for now.